Oh, I got 300 subs? I was sitting at 299 for a long time. Thank you. Does that mean YouTube is going to send me one of those plaques with the play button? I think I need to get 10,000 or something like that, or 100,000 to get the plaque. Yeah! Hello. Yeah. So, my dogs have been having diarrhea, and I was practicing. Um, I was practicing speaking Spanish with my friend, and um, do you ever are trying to speak a foreign language and you like talk yourself into a corner and you get to a spot where you you don't know how to say what you're trying to say, but then you also don't know how to back out and talk to about something else. So it's like you talk yourself into a corner and it's like, oh, where do I go from here? And uh, so I was talking about my dogs, and I don't know how to say diarrhea in Spanish, so I had to get creative, and I said I said ellos hacen un jugo de caca, which means so I had to get creative. So that I said they made poop juice. So I thought that was pretty creative. So I was able to talk myself out of the corner and get through what I was trying to say. Um, okay. So let's go ahead and get started. Um, so today uh, we are going to discuss today we are going to discuss energy and rotational motion. Tengo esperanza que ustedes no hacen jugo de caca también. Porque no es divertido. All right. Energy and rotational motion. So we've already learned a little bit about energy and rotational motion. We learned about the kinetic energy of rotation, which is 1/2 I omega squared. And we learned that if something is rolling, then it has both rotational and translational kinetic energy. Okay, so that the total kinetic energy of something is rolling, and I went through all the derivation of this. It's 1/2 mv squared times the quantity 1 plus I over mr squared. So basically the 1 term corresponds to the translational kinetic energy, and the I over mr squared is the additional part due to the rolling. Okay, so what I wanted to talk about today is gravitational potential energy if you have an extended object. So if you have an extended object, the gravitational potential energy is still mgy, but the y value, because it's an extended object, the question is, what is the y value that we choose? So does anyone want to guess what is the y value that we choose when we're calculating the gravitational potential energy of an extended object? Type it in the chat if you think you know. The center of mass. You are correct. So we use the y coordinate of the center of mass, and that allows us to calculate the gravitational potential energy of an extended object. Okay. So we're gonna do several examples using this today. All right. So the first example is consider a 4 kilogram rod that is 5 meters long. And uniform. Okay. So it starts out at rest, and it starts out horizontal. So here's the rod right here. It's pinned at its left end, and because it is a uniform rod, its center of mass is located exactly in the center. Okay? It starts out horizontal. Okay? And then it swings to the vertical. Okay? So now the center of mass is down here. So you can see that because the center of mass is lower, it is lost gravitational potential energy, so it's gained kinetic energy. Okay? And so the question is, what is omega when it gets to the lowest point? All right? So to solve this problem, we are going to use conservation of energy. All right? Initial energy equals final energy. All right? And I will call the lowest point, the lowest elevation of the center of mass, I will call that y equals 0. Okay? So we start out with gravitational potential energy. All right? So we start out with mgy, cm, and we end up with rotational kinetic energy only. How come we don't have translational kinetic energy is because the rod is pinned. So something only has translational kinetic energy if it's free to go from point A to point B, where however far away point B is, okay? But this rod is obviously limited in its motion, so it's going to have only rotational kinetic energy because it's pinned, okay? So if we think about this, well, this distance right here, because it's a 5 meter long rod, this distance right here is 2.5 meters. It's a uniform rod, Okay, so that 2.5 meters, it swings down. So we can see that the center of mass is going to undergo this sort of quarter circle arc, and it's going to end up 2.5 meters below where it started. Okay, so when I do my mg, so this distance right here is 2.5 meters. Okay, so my mg/ycm is going to be 4 kilograms times 10 times 2.5. All right, and that equals 1/2 I omega squared. So I got to compute the rotational inertia of the rod. So let me do that. Because it is a uniform rod, that means that lambda is going to be mass per length. Okay, so the linear mass density is going to be constant. So I have 4 kilograms of mass, and the rod is 5 meters long. So that's a linear mass density of 0.8 kilograms per meter, and that's constant. Okay, because, all right, that's a constant because it is a uniform rod. Then I can calculate the rotational inertia. The rotational inertia is going to be the integral of x squared times lambda dx. All right, so the integral is going to go from one end of the rod to the other, so it goes from 0 to 5. And then the linear mass density is constant at 0.8 dx. So I do that integral, I'm going to get 5 cubed over 3 is the value of the integral of x squared dx from 0 to 5, and then I multiply it by 0.8. Okay. 125 times 0.8 is 100. 100 divided by 3 is 33.3 kilogram meters squared. So that was a nice little review of how to calculate rotational inertia. So I'm going to plug that in for I right there. So I have 33.3. And then I can solve for omega quite easily. And I get that omega is going to be 2.45 radians per second. All right. And then I could go on to ask a question like, for example, what is the linear speed of the lowest point of the rod? Okay. What is the linear speed of the lowest point of the rod? So to do that, you could use linear speed is omega times r, where r is the distance from the pivot point. And we can see that the end of the rod is 5 meters from the pivot point because it's a 5 meter long rod. So I would have 2.45 times 5, which is 12 and a quarter, 12.3 meters per second. Okay, so that's a nice example of applying energy to these problems. Now, let me tell you about a really common thing that happens in physics. Okay, this is a nice little problem here, a nice little modification of this problem. What if the rod is not horizontal initially? Okay? What if the rod is not horizontal initially? So for example, so here's the point where it's pinned, okay? And then let's say here's the center of mass. All right. And here's the vertical. So this distance is L, and let's suppose that it starts out at some angle theta to the vertical, okay? So it was really easy to figure out how high the center of mass starts out at when it's horizontal, okay? But it's still pretty easy, but it's a little bit trickier when it starts out at an angle, so I just wanted to discuss that. So it's going to swing to the vertical like this, all right? And so kind of the question is, well, how high was it when it started? Okay, what is this distance right here? All right. So what we need to do is we need to do a little trigonometry. So let's figure out what is that distance right there. And I can see that I have a right triangle. I have this right triangle right here. And here's the hypotenuse of the triangle. And so I want the adjacent part of that triangle, okay? The adjacent part, which would be cosine. So this is L cosine of theta, all right? And this distance is y. Now type it into the chat. What do these two distances have to add up to? Okay, thinking that this thing swings down to the vertical. That's an L, not a 2. They have to add up to L. Very good. All right, and the reason is that the length of the string didn't change. All right, so it's the length of the string is L here. When it swings to the vertical, the length of the string is still L. Okay, so this entire thing is L. So this distance plus that distance have to add up to L. So we have L cosine of theta plus y equals L, which means that y equals L minus L cosine of theta, which means that y equals L times the quantity 1 minus cosine of theta. So this is a little handy-dandy expression for the y coordinate. Okay, so that comes up in physics fairly often, and especially when you're talking about the motion of pendulums and things like that. So let's apply that. So the example is repeat the previous problem. But the rod is initially has a 35-degree angle to the vertical, like that. Okay, so instead of being horizontal, the rod starts out like this. Okay, and then it swings to the vertical. This angle right here is 35 degrees. So what we do is it's the same problem as before. Initial energy equals final energy. The final energy is rotational kinetic energy. Okay. The initial energy is gravitational potential, mg/cm. Now I'm going to use that expression for y that I discussed previously. So I have mg times L times the quantity 1 minus cosine of theta equals 1/2 I omega squared. All right. So now I can just plug in numbers. It's a 4 kilogram rod. The length from pivot point to where the center of mass is was half the rod, so 2.5 times the quantity 1 minus cosine of 35 degrees equals 1/2 times, I believe the inertia was 33.3 omega squared. So this gives us an omega of this gives us an omega final of basically 1.04 radians per second. All right. So we can see that it is less than the previous problem by quite a lot, and that's because it started out with a lot less gravitational potential energy, so it's going to have less kinetic energy when it gets to the lowest point. Okay? Type it into the chat if you know how could you get the most, how should you start the rod out so that it gets the most angular velocity when it gets to its lowest point. All right, type it in if you know. All right, so I'm going to do, while I'm waiting for an answer, I'm going to set up another problem. So we've got a uniform disk of mass 4 kilograms and radius 0.3 meters. Okay, looks like no one wants to answer my question. So basically, to get the greatest spin speed at the bottom, you want to get the center of mass as, oh, there it goes. Excellent. Yeah, so you want it to start, the center of mass to start out as high as possible, which means not horizontally, but you actually put it like this. Okay, and then you give it a little nudge so that it's not balanced anymore, and then that's the highest speed that you can achieve. Very good. Okay. So we have this uniform disk of mass 4 kilograms and radius 0.3 meters. We have a 5 kilogram mass that is at rest to start, which means that the spool is also at rest. And then the mass drops 2 meters. So the question is, after it has dropped 2 meters, what is the final speed? Okay. So we actually did some problems like this in our energy unit. Okay. Excuse me. We did some problems like this in our energy unit. But we didn't consider the mass of the pulley itself. Okay. So here we're actually considering if you have a spool and it's spinning, it has rotational kinetic energy. Okay. So when we did energy earlier in the course, we assumed that the the disk was actually massless, so that it has no kinetic energy. But now we're going to take that into account. All right. So we start out with initial energy equals final energy. Okay. The initial energy is the gravitational potential energy of this hanging mass. We are not going to include the gravitational potential energy of the disk, and the reason is that the disk it's maybe tied to the ceiling or something. It's a spool, so that the spool itself isn't moving. So its gravitational potential energy is constant. Okay, so we'll just call that gravitational potential energy 0, and we will only consider the initial gravitational potential energy of this mass. Okay, so we start out with mgy, and this m is little m. Okay, we end up with kinetic energy. This mass that's falling has translational kinetic energy. It's not rotating while it falls. Okay, so we have 1/2 mv squared. All right, but then as this thing falls, that means that the spool is going to start spinning. Okay, so we also have the rotational kinetic energy of the spool. All right, now the fact that it is a uniform disk means that we have a formula for its inertia, and I'm not going to derive it. You could derive it based on what we learned in the lesson about rotational inertia, but if you have a uniform disk, it's 1/2 m r squared is the inertia. Okay, so this m is a different m from that m, so that's why I wrote it as Majin M from Dragon Ball Z, and that refers to the mass of the disk. Okay, so going to the next line, I'm going to plug that in. So I have mgy0 equals 1/2 mv squared plus 1/2 times 1/2 m times r squared omega squared. Okay, now I kind of separated out r squared omega squared. Now because just like rolling, this spool is unwinding. The speed at which the spool unwinds is related to how fast the mass is dropping, according to the usual relationship, which is V equals R omega. Okay, so it's the exact same equation as you get when something is rolling, which means that V squared equals R squared omega squared. So I can see I have R squared omega squared right there. So I have mgy0 equals 1/2 mv squared plus 1/4, because it's 1/2 times 1/2 big M v squared. Then I can collect like terms, factor out the v squared from both of them. So I have 1/2 little m plus 1/4 big M times v squared, mgy0. Now I can plug in numbers. 5 times 10 times 2. 1/2 of that is 2.5. 1/4 of that is 1. There, we can solve the problem. We get that the final speed is 5.3 meters per second. All right. So now, those are the examples for today. So I have like one more really brief thing, and that is about rotational work. All right. So you might recall that the formula for work is the integral of force times displacement from initial position to final position, okay? So the work done by rotations, we're going to use an analogy, okay? So type it into the chat if you know what is analogous, what is the rotational analog of force, and what is the rotational analog of linear displacement. Type it in the chat if you know the answer. There's a question. Yeah, there's no spring. No spring. It's like a toilet paper roll unwinding. Okay? Yeah, torque and angular displacement. Very good. So the rotational work is the integral of torque with respect to angle from initial angle to final angle. Okay, so this, just by analogy, this is the work done by a torque. And you can actually derive it. I'm not going to do it. I'm just going to use the analogy. So this form is really useful if we're talking about the automotive industry, because engines exert torque and they rotate things. So if you want to know how much work is the engine doing, you could use this formula. All right. So that is my lesson for today. It's a pretty quick lesson. I will see you in the Zoom room with some announcements. Okay? Bye for now.